Well, we're going to keep working with right triangles today. And tomorrow we'll move on and do some applications, but today we're just kind of laying some groundwork for the rest of the semester. All of trigonometry for all types of triangles is really based on the trigonometry of right triangles, so it's good to take our time going through this and make sure that we've got a good foundation. We're going to kind of do the opposite of what we did yesterday. We're going to, yesterday we became familiar with the 6 trigonometric ratios. Today we're going to work with the 6 inverse trig relations. In addition to that, we're going to solve more right triangles today, but the case that we didn't look at yesterday, we always assumed yesterday that we had one angle given, one of the acute angles. Today, we can work backwards, and even if we don't know either of the acute angles, we can still determine what the unknown angles are as long as we know 2 sides. So that's what we're going to work with today. We kind of completed half of basic trigonometry yesterday. Today we're going to complete that with the other half. Okay, well here's the principle of everything that we're going to be doing today. First of all, we know that for every acute angle theta, we can find the sine, cosine, and tangent ratio using the calculator. If we know any angle, we can type in that angle, hit the button, and wham, it'll tell us what the ratio is. Well, what we want to do today is we want to work backwards so that if we know what the ratio is, we can work backwards to find the angle. Opposite thing, opposite direction of what we did yesterday. Now, here's the principle that we're going to operate under, and this is basically notation, how we represent this. If we know that sine of theta is equal to x, then we can say 2 things. The first thing that we can say, the first thing up there on the screen, is that theta is equal to the inverse sine of x. Now, sine is kind of a, all the trig functions, the notation is very important. So we're going to spend just a couple of minutes now making sure that you understand the way that things are written, because slight variations in the way you write something can give it an entirely different meaning here. For example, if we know that sine theta is x, we want to get theta by itself. We cannot divide off sine. Why can't you divide off sine to get theta by itself? If you write that, or this, or that, you know what you've got? Nothing. You've got that. You've got a ruler with no markings on it. It's useless. Okay? You're saying that you've got a ratio, but you don't know what the ratio is for. These functions are only good if we've got some value to associate with it. On their own, they are useless. So to claim that we could divide off sine, we can't do it. We can't divide off sine because sine on its own has no meaning. It's worthless. So we want to get theta by itself. What we have to do is we have to apply another tool, an inverse function. Back in Tech Math 1, we worked with inverse functions. They reverse the role of a function. So what we do is we apply the inverse sign to both sides. We can say that the inverse sign, we're going to apply that to both sides, of the sine of theta is equal to the inverse sine of x. We're applying inverse sine to the left of both sides of this equation. Inverse sine of sine theta and inverse sine of x. Now, over here, the inverse sine of sine, what do you suppose these two do? They cancel each other off. They negate each other. This, we input the angle and get out some ratio. This puts it back in terms of the angle. So we end up with theta on the left side is equal to inverse sine of x. Now another way to write that is that we can say theta is equal to arcsine of x. These two things mean the exact same thing. I like to think of ARC as the angle whose sine is x. So if you see the arcsine of x, what we're really looking for is the angle whose sine is x. Arctangent would be the angle whose tangent is x. Now, I put a note up here, be careful of common errors. There's 2 very common things that I see written that are mathematically not sound. One of them is this. We already discussed one of them. It's untrue to say that if sine of theta is equal to x, that theta equals x over sine. Okay? Because this has no meaning. It's just 3 letters. It has no mathematical meaning at all. So don't make that mistake. The other mistake that's often written is in regards to this. If we know that theta is the inverse sine of x, that is not by any means equal to 1 over sine of x. What is 1 over sine of x? We have a name for 1 over sine. It's cosecant, and that is not the same as the inverse sine. We say this is the inverse sine or the arcsine. Be careful of those two things. The difference is this. When you have this function, when you have the sine function, what do you plug into it? You plug into an angle or a ratio. An angle. You plug in an angle, and then you hit the sine button on your calculator, and what does your calculator tell you? It tells you a ratio or a numeric value. But the inverse trig functions do the opposite. Those, we put in what our ratio is, and it reports what the corresponding angle is. It does the reverse of this. This takes our angle and tells us what the ratio of opposite over hypotenuse is. Here we have to type in that ratio, and it'll tell us what the angle is. The two natural consequences of this to complete the discussion is that if the cosine of theta is equal to y, then theta is the inverse cosine of y. Or in other words, theta is the arc cosine of y. And if the tangent of theta is equal to z, where again z is a ratio, then theta is the inverse tangent of z, or the arctangent of z. Okay. We'll use these and look at how they apply to the calculator in just a second. But this is the point that I was just making a minute ago. Take this statement. Again, this is still notation. We'll get to some triangles in a minute. But suppose we know that the tangent of theta is equal to x. Note that theta is always an angle. It could be in degrees, it could be radians, it could be revolutions, but theta is always an angle. Whereas x is always the decimal equivalent of the opposite divided by the adjacent. The trig functions always assign to some angle a ratio. Think about it like this. Over here we've got angles. Over here we've got ratios, or in other words, decimal. What are the units on angles always? Well, we just said it. Radians, degrees, or possibly revolutions. What are the units on our ratios that the calculator reports? There are none. There's no units on this ratio. So in order to get from here to here, we might use tangent cosine theta or sine theta. But what if we need to get back? What if we know the ratio and we got to use the angle? Well, then we're going to use one of the inverse trig functions. Tangent of theta always assigns a ratio to some angle, whereas the arctangent always assigns some angle. In other words, if we have the ratio and we want to go back, now we're going to use arctangent of x, arcsine of x, or arccosine of x. Now, it's worth noting that we're going to have a little problem going back. Because for every angle that you type into your calculator, you're going to be able to find the ratio. It'll never be a problem. However, going backwards, there are always many different angles that could have the same ratio. We're going to work with that next week, and it's important to note now, because when you do the homework today, you're going to be working back in the direction, but we're only finding one solution that the calculator reports. There's always many different solutions, but your calculator only gives you one of them. We'll just leave that idea there for now, but we'll come back to it. Okay? Now, your calculator has to be in the correct mode when you type in your angle, right? That's what we talked about yesterday. You have to be in either degrees or radians, as the case may be, before you hit the trig button in order to find out what the ratio is. Now, the opposite has to be true. When you type into your calculator what a ratio is and you want to ask what the angle is, you have to be in the correct mode. It's going to report the angle in whatever mode your calculator's in. So if you're in degree mode and you use one of these three, your calculator will report your answer in degrees. All right, well, let's do some examples. Let's work with some triangles. We've got a triangle here. Now, this case is different than what we've done so far in that we know none of the angles except for the 90-degree angle, the right angle. Okay. We just want to find the angles. We won't find that missing side at this point. We just want to find our angles. So you need to decide on an angle that you want to choose to be your reference, so we can label all three sides like we did yesterday. You can choose either one. Let's choose, just for convenience, let's choose the one on the top right. We're going to let this be theta. Now, based on that, we can only find theta if we know two sides relative to that angle. What two sides do we know relative to that angle? Opposite and hypotenuse. So we know that the sine function is the one we're going to use, and we can conclude that the sine of theta is equal to the opposite, 4.125, over the hypotenuse of 8.700. Okay, well, we can divide that to find out what that ratio is, and we know that the sine of theta will be equal to 0.4741. So now we apply the inverse sine function to both sides. Inverse sine of sine theta is equal to the inverse sine of 0.4741. Now on the left side they cancel off. We've got theta equals inverse sine of 0.4741. Take your calculator. Type in your ratio. Now we know the ratio. We want to know what the corresponding angle, the angle that will yield that ratio is. 0.4741. We want to find our angle. At this point, we haven't committed. We could find our angle in degrees or radians, but let's go with degrees. So make sure your calculator's in degree mode. Now, when we ask it what angle has a sine value of 0.4741, it'll tell us in degrees. You're going to use the most calculators, it's the second function key or shift key right above your sine function. So 0.4741, 0.4741 inverse sine, and it'll tell you the angle that yields that. I have, well, what'd you get? Go ahead and do that. 28.3 degrees. That's what you should get. Take just a minute. Everybody get 28.3 degrees. I'm just going to take a minute and make sure. Yeah, we should. Thanks, Aaron. 28.30 degrees. What'd you get? So we got our angle of 28.30 degrees. Now, we can find this angle one of two ways. What's the easiest way to do it at this point? Subtract. 90, these two have to add up to 90 since 90 degrees is already used there. 90 minus 28.3 is 61.70 degrees, and we're done. We found both angles. However, if we just wanted to find out this angle using trigonometry, what two sides do we know relative to this angle? Let's go back and call that beta. Yeah, we know adjacent and hypotenuse, so we can say that's the cosine function. Cosine of beta is equal to 4.125 over 8.700, which means the cosine of beta, whoops, we already figured out what that is. Cosine of beta is 0.4741, which means beta is equal to the inverse cosine of 0.4741. Take a minute and do that on your calculator. 0.4741 instead of inverse sine, let's find the inverse cosine. And you better get, it's just another Greek letter. Theta is the most kind of, sort of like we always use x as the variable in most algebra equations, but you can use other stuff. We usually use theta for angles, but we can use other stuff. Did you get 61.7? Should round to 61.70, so it works out. Okay, we can find that either way. The advantage of doing it by subtraction is it's quick. The advantages of doing it this way are, if that was wrong, this one would be wrong. Here we're using given information. Again, it's always nice to use given information if possible. That eliminates error. All right. Let's do one more, and then we're going to go on and look at the other three trig functions. We've got another right triangle here. We want to find the unknown angles and the unknown side. Okay, we got to pick an angle as our reference. Let's just choose the one on the left. Wouldn't have to. Now, to find that angle, what trig function do we have to use based on what we're given here? Got to use tangent because we know the opposite and we know the adjacent. So we know that the tangent of theta is equal to opposite of 16.75 divided by an adjacent of 8.50. We would apply the inverse tangent to both sides. On the left side it cancels off, and so we're left with theta being equal to the inverse tangent 16.75 divided by 8.50 is 1.9706. What'd you come up with for an angle there? You have no work to do. You just need to go back, do that again on your calculator, but make sure that you are in radian mode, and it'll report the angle in radians. 63, that better be a little bit over than a radian, a little bit more than a radian. Radian's around 57 degrees, so I'll bet you it's 1 point something. 1.10 radians. Good. 1.10 radians. Now, finding the other angle, here there's definitely a better way to find the other angle. We can do it by subtraction, or we can go back and use trig functions. But if we wanted to find this one, what trig function would we have to use now? Let's call this one beta. You would still use the tangent function, but they're going to be reversed. We know that the tangent of beta would be opposite of 8.50 over 16.75. Okay, well, that means that beta is equal to the inverse tangent of 8.50 divided by 16.75. 0.5075, yeah. And again, I'm going to make sure I go into radian mode here. What is beta in radians? How about 0.47 radians? There it is. Now, what has to be true about theta and beta in this case? If we're in radians, all three of these angles, a little review from yesterday, if you're talking about radians, all three angles have to add up to what? Pi. Now, that 90 is pi over 2, which means these two have to add up to half a pi. 1.10 plus 0.47 This is just kind of a check. This isn't necessary for the problem. Theta plus beta is equal to 1.10 plus 0.47. 1.7, that's pretty close to half a pi, so we're good. It works out. Now, we still aren't completely done with the question. We have one very small thing to finish out yet, and that is to find that missing side length. Now, what would you use here to find that missing side length? Use the Pythagorean theorem. Absolutely. We could find the missing side length as we did yesterday by knowing this angle in a trig function, but we can use Pythagorean theorem. So we know that we'll call this side C. C squared Yep, 18.78. Yep. $18.78. And we're done. We found all the angles, we found all the sides, we completed the triangle. Here's the bread and butter of what you need to know about inverse trig functions besides sine, cosine, and tangent. Arccotangent of x is equal to the arctangent of 1 over x. And here's why. I'm going to draw you a picture to help you remember this. Let's take this triangle and call that theta. We're going to make this side 1 and this side x. Now tell me, what is the tangent of theta in this triangle? That's right. In this triangle, it is definitely true that the tangent of theta is equal to 1 over x. Everybody agree with that? Okay. Well then, what is the inverse tangent of 1 over x? Or in other words, what is theta? Theta will be everybody agree with that? That has to be true. Well, I'm just going to write that another way, just so that you get used to the notation. These mean exactly the same thing. It's also a very minor point to make here, but make sure that if you use, I usually use this notation just because it's a little bit shorter and it's what's on the calculator, and for me it's easier to think about. If you decide that you want to go the arc function route, make sure that you use a lowercase a. Capital A has a slightly different meaning. We'll just leave it at that for now. Make sure you're using a lowercase a. Okay, well, let's go back to that triangle for a minute. Tell me, what is the cotangent of theta? Cotangent of theta is not opposite over adjacent, but adjacent over opposite. So theta or in other words, we can say that the arc cotangent of x is equal to theta. Everybody agree with those two statements? Yeah, we just reduce it. Well, there you go. This is theta expressed two different ways. And so you can conclude that arc cotangent of x is equal to theta, which is also equal to arctangent of x. So when we've got to evaluate an inverse trig function of one of those three lesser desirable cousins, we have to take the reciprocal of that ratio first, and then we can evaluate it using your calculator. Now, the three corollaries to that are, as you might suspect, the arcsecant of y is equal to the arccosine of 1 over y. And the arccosecant, or inverse cosecant, of z is equal to the inverse sine of 1 over z. Now, what we're going to do next is just look at some expressions and practice doing them on your calculator, because that's a little confusing. Let's do some examples. Now, again, I made this note earlier, but it's an important note to make at least, that when we evaluate inverse or arc functions, there's more than one answer. In fact, there's always two real important answers and hundreds of others. But the one that we're doing today, is always going to be what's called a principal value. That is the easy one to find that your calculator tells you. Your calculator always tells you the principal value. Next week we're going to see how you find the other ones and why they're important, but we don't need that just for solving right triangles. So let's find the inverse cotangent of 0.6811. Okay, well first of all, before you go to your calculator, just write it out. We have to first to get that in terms of sine, cosine, and tangent, or inverse sine, inverse cosine, or inverse tangent. You would write this as the inverse tangent of what? The reciprocal. Remember, this is a ratio. This is the ratio of, for cotangent, adjacent over opposite. But we want to work with tangent instead, so we need opposite over adjacent. That means that we take this and flip it upside down. We basically flip it so that it becomes opposite over adjacent, or the tangent ratio. Take your calculator and evaluate inverse tangent of 1 over 0.6811. We'll answer these in degrees, incidentally. For these first four, we'll just do these in degrees. Anybody get it? That's right. 55.74. We're going to do a bunch of these, real short examples to make sure you're using your calculator correctly. Any of these that you don't get to work out, put a little star by or jot them down in your notes, scribble it down. We'll look at it right after class. Okay, let's do another one. Arcsecant of 1.6831. Well, how would you rewrite arcsecant of 1.6831? We want arc cosine, so I'm going to write it like that. That's the same as arc cosine. Arc cosine of? So 1.6831 here, again, you can save yourself a few keystrokes on the calculator if you use your reciprocal button. Type 1.6831 inverse, and then hit the inverse cosine. I have 53.48. Anybody gets 53.48? Oh, I must have missed a digit. 5.5. Have to deduct that from my score. Okay? 53.55. All right? And another. Here, the cosecant of theta equals 2.6850. So what is theta equal to? It's the inverse cosecant of 2.6850. Agree with that? If cosecant theta is 2.6850, then theta must be the inverse cosecant of 2.6850. That's all well and good, but now you got to evaluate that. That means theta is not inverse cosecant. That's no good. We're going to have to write it as inverse sine, its reciprocal function of the reciprocal, 1 over 2.6850. What do you get there? $21.87. That's right. Okay, one more. Tangent of beta is 3.100. Well, then what's beta equal to? Inverse tangent of 3.100. Do you have any switching you need to do here? No. You will learn to like sine, cosine, and tangent very much. And you'll learn to think slightly less of cotangent, secant, cosecant. Well, inverse tangent of 3.100, you can just do that on your calculator directly. It's already in terms of inverse tangent. That should give you 72.12. There they are. Oh, we're not done. Let's do a few more of those. They're fun and important. Now, these we're going to report in degrees and radians. Let's just do a couple more, then we'll wrap up. Let's find the inverse secant of 2.7830. That's the inverse cosine of 1 over 2.7830. That you can crank out. Now, the easy way to do this is to not do the problem twice, but to do the problem once in degree mode and then just use your calculator to convert it into radians. If you do this with degrees, anybody get it with degrees? You should get 68.94 degrees. Will I verify that? 68.94. How do you know what to take the reciprocal of? You mean this or that? When we've got either cotangent, inverse cotangent, inverse secant, or inverse cosecant. If you've got sine, cosine, or tangent, those buttons are on your calculator, so you can just evaluate them directly. But these, we have to get them in terms of something that is on your calculator. Secant's not on your calculator, so we have to rewrite this as inverse of cosine, which is more workable. But remember, cosine and secant are reciprocals of each other. So if we want to work with cosine, we can do that, but we got to take the reciprocal. Make sense? Okay. 68.94 degrees. Anybody get that? Verify that? Okay, good. Well, then just take your calculator and bump it into degree or into radian mode. Another skill that's good to be able to do. Bump that into radian mode, and you should get 1.20 radians. Now, it's also good to get in the habit of thinking in terms of radians. General rule of thumb, not good for conversions, but just an estimate, there's about 57 degrees per radian. So if you get an answer of 68.94 degrees, you should be anticipating a result of a little bit more than a radian. Arcsine of 0.111. Now, do we need to take a reciprocal here or not? Grant, this directly addresses your question. No. Arcsine is the same as inverse sine. You can just do that directly. You should get 6.38 degrees. What'd you get for radians? 0.111 radians. Pure coincidence. I had that too, and I started to doubt myself. I thought, boy, did I just miss something? But it's coincidence. Okay, well, let's do one more. Sine theta is 0.9920. Sine theta is 0.9920, so theta is the inverse sine of 0.9920. How many degrees is that? 82.75 degrees. which is pretty darn close to, if you bump that into radians, 1.444 radians. Okay, well, you'll have plenty of practice on that. A large part of the homework is just evaluating those short little expressions, making sure that you are skilled at doing that. The last one thing that we need to do is we need to look at two special cases of relationships. Trig functions are related to one another based on the triangle. And these are, I'm going to show you a couple of very short little relationships that are not vitally important for the purposes of solving triangles, but it's a good time to at least recognize them. Okay, the first one, for any acute angle in a right triangle, let's just take a right triangle and make up some angle down here. Now, if this angle is theta, what is this angle? That's right, it's 90 degrees minus theta. Everybody agree with that? Okay, well, let's just label these A, B, and C. Now tell me, on this triangle, what is sine theta? Opposite over hypotenuse? It's B over C, right? Okay. Well, now let's switch our reference. Let's stand at this angle. What is B over C in terms of this angle? It's the cosine now, because B over C from this angle is adjacent over hypotenuse. So B over C is the sine of theta, but it's the cosine of 90 minus theta. The sine of some acute angle is always the cosine of its complement. This is why, for those of you who are in the electronics programs, sine and cosine waves are always 90 degrees out of phase. Here's why. Because one of them is always 90 degrees off from the other one. It's also true, though we won't look at the picture, that all the cofunctions have this property. The tangent of theta is equal to the cotangent of 90 degrees minus theta. Secant of theta is equal to cosecant of 90 minus theta. Now, take just a minute and verify this with your calculator. Just take your calculator and take the sine of 5 degrees. What is the sine of 5 degrees? Let's go 4 decimals on that. You should get 0.0872. Now that better be equal to the cosine of what? 90 minus 5, or in other words, 85 degrees. Check it. What is the cosine of 85 degrees? Works out. That'll always be the case. So in fact, if your sine button breaks on your calculator in the middle of a test, don't panic. Just any angle that you want to find a sine for, subtract it from 90 and use your cosine button. Hopefully that won't happen. But it's out there. Okay. And the last interesting relationship between sine, cosine, and tangent is this. The tangent of an angle is the sine of that angle divided by the cosine of that angle, and here's why. We're again just going to use a generic right triangle with an angle theta. Now, what is the tangent of theta here? A over B. Agree? Okay. Well, what is the sine of theta divided by cosine of theta? Sine of theta is what from this triangle? A over C. The cosine of theta is B over C. Now, you remember how to reduce a compound fraction where you've got a fraction within a fraction? You're taking one fraction, dividing it by another, so you're going to take A over C times the reciprocal of B over C. So we flip it and multiply times C over B. But what happens to the C's? Boom, boom, and you're left with A over B. And what's A over B equal to? Tangent of theta. These are called trig identity, and there's dozens of ways that these different angles are related to each other. We're just looking at the two that are easiest to see from a right triangle. And here's the last one. Here's today's grand finale. The sine squared of an angle, or the sine of an angle squared plus the cosine of that same angle squared will always give you 1. Here's why this one's true. Pythagoras knew what was true about that triangle. That's right, a squared plus b squared was equal to c squared. That was known a long time ago. Now here's what we're going to do. We're going to take and divide every term in that equation by c squared. So let's divide that by c squared, divide that by c squared, and divide that by c squared. Don't you agree that the equation is still true? Okay. Well, this becomes a over c squared. This becomes b over c squared. And c squared over c squared is 1. Well, go back to that triangle and our angle theta. What is a over c? It's the sine of theta. B over c is cosine of theta. And so we write it in that form. We know that the sine squared of some angle plus the cosine squared of some angle equals 1. Okay. Now, what we've accomplished is we've laid all the foundational work for right triangle trigonometry. The stuff that we've done in the last 2 days, we're going to be referring to for the rest 5 weeks. Tomorrow we're going to start some applications, just do some problems involving right triangles, and then next week we'll move on to triangles that don't have right angles in them.